So up to the last class we have discussed what happens, all right? So how actually basically the liquefaction occurs, right? How liquefaction occurs and what is the basic mechanism behind that, right? So we see that when sand or soil is vibrated, all right? So it is vibrated. So there is one oscillation given to the sand. It tends to collapse, it tends to densify, all right, or it tends to reorient and rearrange itself into a denser packing. So that is the behavior of the soil. Again, the water, what we have seen that it undergoes vibratory motion. It undergoes, there is waves generated in the water body, and the water molecules, they start vibrating. So what happens is that the water tries to escape from the soil mass, whereas the soil mass compresses and tries to compact into the water mass. So the two forces, they interact with each other, and the pore water pressure shoots up, and when it increases to such a significant amount that the effective stress in the soil, it almost becomes zero, or it almost becomes negligible, all right? So even a small amount of shear which is applied by the earthquake motion, or if there is any static loading also there, all right, that is enough now to cause constant deformation of the soil, and the soil, we say that it is liquefied. So this term liquefaction, it was first described by Arthur Casagrande, all right, so in 1936, all right, Arthur Casagrande, in 1936, he described this, all right. So he initially described it in terms of the critical void ratio that we have discussed in our soil mechanics class, but we will see that again in this class as well. But then it was seen that there was a static flow liquefaction failure in the upstream slope of Fort Peck Dam in 1938. All right, then the study intensified, and what happens during the vibration load, all right, so there is rolling of the soil particles over each other. So that part of the simulation in the laboratory was done after 1938, and Middlebrooks 1942 actually did a considerable amount of research into that. And the attention to this study, that is soil liquefaction study, it was intensified mostly after the disastrous consequence following earthquakes in Niigata. Niigata is a coastal city in Japan. All right, so it is near the coast, so we can say that it is, of course, since it is coast. So first of all, there is sand. Secondly, there is high water table. All right. So all of the necessary conditions required for liquefaction was present there. And after, there was an earthquake in Niigata in 1964, and there were significant soil liquefaction was observed in Niigata, Japan, as well as in Alaska. We have already seen some of the pictures and videos in the previous class. So I will share the video as well of that. So this is a brief history of liquefaction as a subject or subject matter, all right, or as a research topic, all right, soil liquefaction. Now Assam has its share of liquefaction, all right, in Bihar 1934 as well. So you can see before Arthur Casagrande published his research work on liquefaction, before that itself, Bihar in the earthquake in Bihar. So there were liquefactions observed. Of course, at that time it was not known as liquefaction, and obviously we will see how. So in Assam in 1897, then in 1950, so the Great Assam Earthquake of 1897. So this is obviously one epic, I mean, proposition as far as earthquakes are concerned. We are concerned with earthquakes. So this is one of the greatest earthquakes that ever occurred in the world. All right. So you can look into that. So significant amount of devastation followed. So here I have one article by Dr. Jugal Kalita, and it was actually translated to Assamese by Bipul Soikia. So here you see, so at the time Nolbari, so the Kamrup DC, Kamrup Upayakto, so that is, he was staying at Nolbari, right? So he was staying at Nolbari. So his name was Mr. P.R. Gordon. So he was definitely British at that time. So he was staying in 1897. So he was staying at Nolbari at that time. So from his rest house, all right. So from his rest house, he could clearly see, all right, ভূমিকম্পৰ তৰংগবোৰ দেখিছিলে. So you note this line, all right? ভূমিকম্পৰ তৰংগবোৰ দেখিছিলে. That means he could observe the waves, all right? And where he could observe the waves, you can see rest house of ওচৰৰ প্ৰকাণ্ড পথাৰখনত. So it is field, it is a field, so soil, all right? So on soil, on a soil mass, he could see the waves traveling, all right? এটা তৰংগৰ আন এটাৰ পিছে পিছে যোৱা দেখিছিলে, আৰু সেই তৰংগবোৰ গতিৰ লগে লগে পথাৰত থকা ধানবোৰ, আহু ধানবোৰ একোবাৰ ওপৰলৈ উঠিছিলে আৰু একোবাৰ তললৈ নামিছিলে. Right? So that is paddy field. So the Kamrup DC who was staying at Nalbari in his rest house, from his rest house he could observe the waves of the earthquake on a paddy field. Right? So you can, you can visualize how much energy and how much, this effect the particular earthquake caused. All right. লগে লগে পথাৰত থকা আহু ধানবোৰ then cracks and features, all right. ফাটবোৰৰ পৰা 3 ফুটৰ পৰা 4 ফুটলৈ পানী. So you can see, so there were springs in the paddy field. Obviously it was with sand and other things, so that was basically due to the liquefaction, all right. So the pore water pressure at the depth, all right, so it got increased, and then after the earthquake it shoot up, all right, and through the cracks and the fissures in the paddy field it shoot out, all right, the water shoot out, all right. You can see the bali aru pani দুইৰে পৰা 12 ফুট উচ্চতালৈ. So 12 feet in some places, all right. So it was significantly high amount of pore pressure generation. Then again you can see here in Guwahati, all right. So in Guwahati you can see, first of all, there were waves in the Brahmaputra, all right, in the river Brahmaputra, and all the river banks were inundated, all right, so it was flooded. The waves, from the waves of river Brahmaputra, নৈৰ কাষৰ পথ ঘাটবোৰ বহু ঠাইত পানীৰ তল গৈছিল, right? কেইবা ঠাইতো পানীৰ পুং কিছুমানৰ সৃষ্টি হৈছিল, আৰু পোৰ্টলেণ্ড চিমেণ্টৰ ৰঙৰ মিহি মিহি বালিযুক্ত পানী বুৰবুৰাই ওপৰলৈ উঠি আহিছিল. So you can see, so he has given a description in his own word. In his own word, he has given a description of a quicksand condition. All right. And it continued up to 24 hours. All right. So much of pore pressure was generated. It continued. It was not dissipated up to 24 hours. That quicksand condition. All right. That sand boil. It continued. All right. Similarly, in Gwalpara also, the Brahmaputra, all right, so there were 10 feet waves, all right, 10 feet waves which was created in Brahmaputra, all right, and then the marketplace are all of Pokigor, all right, all this brick masonry houses, all right, so everything was damaged. So this is actually one article. It was published in American Ohom Society Potrikar 1990 Hongkhat, all right, so it was published there, and people Jodi Soikia, he actually translated this. So of course there are many other articles of the 1897 earthquake, all right, so it is one of the greatest earthquake to ever occur in the world, right, and it occurred in Meghalaya. It actually occurred in Meghalaya. The epicenter was in Meghalaya, right, and it devastated Assam as such. So this is one picture of a sand boil, so you can see the size of the sand boil. All right, so the cracks and other things are mainly because you can if you go to a paddy field, you will notice that there is one layer of silty clay on top. All right, silty clay on top, and then there is sand. All right, then there is sand, so there is saturated sand. So that is saturated sand. So what happens is when this sand liquefies, it comes out, all right, and there are cracks in the upper layer, all right, and then the sand boils up. After the dissipation of pore water pressure, there is huge amount of settlement, right? So there is huge amount of settlement. So that is why you can see, all right. So these are the vents from which the pore pressure was released, all right. There was sand boil. So the first criterion for liquefaction of soil was proposed by Arthur Casagrande. All right. So in 1936, Arthur Casagrande, 1936, he proposed the criterion for liquefaction of soil based on the critical void ratio. All right. So we have already learned what is basically the critical void ratio. So when we shear the sample, so if it is normally consolidated soil, we go on shearing. All right. We go on shearing. So this is the shear displacement. So when we go on shearing, that sample, the soil sample, when we will shear the soil sample, that soil sample will consolidate, right, or it will get compressed, right. So it will undergo compression, and then we will attain one steady state where there will be continuous deformation, all right, and the shear stress required to cause the deformation will stabilize at that value, all right. So if this stress is applied continuously, now there will be a continuous amount of displacement without any volume change, all right. So no volume change from this particular point. So this point is called the critical void ratio, all right, or the void ratio at this point. Basically the void ratio at this point is called the critical void ratio. So when there is a normally consolidated soil, so we can see there are huge numbers of pore spaces, so there are huge numbers of pore spaces. Okay. So when we shear the soil, what happens, the soil collapse into this, the soil particles, they reorient and arrange in themselves into a denser packing, all right, and these pore spaces, they get reduced, the pore spaces, they get reduced. Now there will be a constant shearing at this particular volume, or we can say at this particular void ratio, so that is the critical void ratio. Similarly, if we shear a dense sand, so dense, there is less amount of voids, right? So what will happen is that the particles will roll on top of each other, right? So they will roll on top of each other, they will try to expand. So you can see as soon as we shear the sample, the void ratio gets increased, all right. So the void ratio, the volume of the soil gets increased, and there is an increase in the void spaces in the soil. The volume of the soil solids will remain same, only the volume of voids will get increased. So here we shear the dense sand sample, and as soon as we go on shearing, and there will be a peak value, All right, so there will be a peak value, and after that it will reduce, and then again it will shear at a constant shear stress or deviatoric stress. And similarly, here also what will happen? First of all, there will be slight amount of compression, all right, and then the soil will expand, 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 all right, and then when it reaches this steady state, all right, from there onward, it will continuously deform at a constant volume, all right. So ultimately, if the confining pressure for both the tests is same, so if the confining pressure is for both the tests is same, we will come to the same void ratio for the same. If the soil types are same, we will arrive at the same void ratio for the two types of test, for the two types of sample. So that void ratio is called the critical void ratio. So we have a loose sample, right? So if we do a drained test, so the loose sample will compact, right? The loose sample will compact. So this is a drain test, right? Whereas if a dense sand is tested under drained condition, all right, so the void ratio will increase. Now, alternatively, Arthur Casagrande, what he said is that since normally consolidated soil, they tend to compress while shearing in a drained condition. If it is undrained condition, there will be development of pore water pressure. All right, so the soil will try to get compressed. All right, it will try to the void ratio will try to reduce. All right, the soil will try to get reoriented or rearranged in a denser state, but the water inside the soil, it is not allowed to drain out, so the void ratio of the soil, it cannot get reduce, it cannot consolidate. So there will be an increase in the pore water pressure. Now when there will be an increase in the pore water pressure, we all know effective stress is equal to total stress minus pore water pressure. So when there will be an increase in the pore water pressure, there will be a decrease in the effective stress, the total stress remaining constant. So what will happen? From the loose state, the state of the soil will move in this direction. From the loose state, the state of the soil will move in this. That means the effective stress, as the pore pressure will go on increasing, the effective stress in the soil will go on decreasing. Whereas, if a dense sand is tested, what will happen under undrained condition? It will try to increase in volume. All right, so the void ratio will try to expand. Since we are not allowing any drainage, so the void ratio, the void ratio cannot increase. So there is no drainage of water into the void ratio, and therefore the pore water pressure will now decrease. All right, so delta U in this case will be negative. So since the pore water pressure will decrease, delta U is negative. So what will happen? The effective stress will increase. Total stress remaining constant. So now what will happen is that since U is negative, so this will become positive. All right, or we can say, what we can say is there will be a positive delta U. Right? So that means positive means I will write it in a better way. Here what will happen is that is minus of delta U. Right? So delta U is negative, right? So negative it will become positive, and it will aid in the increase in the effective stress. So the effective stress will increase for a drain case, for a undrained case of a dense sand. So using this criteria, all right, using this concept Casagrande in 1936, he proposed that if a soil, all right, so here we have the soil, so we have the void ratio, all right, so there is an compression in the soil or normally consolidated soil, loose sand or fine grained sand before shearing, and after shearing the void ratio is decreased. On comparison to the dense sand, so here we see there is less pore spaces, all right, so as soon as it is sheared, all right, so there is increase in the volume and we can see the pore space increase. Of course, this is for the drained case. For the undrained case, so since this will compress, try to compress, so it cannot compress, so therefore there will be positive pore water pressure developed, right? So delta U will be positive, so there will be an increase in the pore water pressure. So now the pore water pressure will be U plus delta U, whereas here the soil will try to expand. Let's in the undrained case, the soil cannot expand. Alright, since it cannot expand, the pore water pressure will be negative. So the pore water pressure, excess pore water pressure generation will be negative. So what will happen is that the pore water pressure in the soil will decrease. Alright, so this was the initial hydrostatic condition. So the additional excess pore water pressure is negative. Alright, so it is trying to pull the soil particles together. All right, it is trying to hold the soil particles together, the excess pore water pressure. All right, so that is why it is reducing the pore water pressure. Here it is trying to prevent the compression. All right, so it is pushing the soil particles away from each other. All right, so there is a positive pore water pressure. So here we have, so if we shear the sample in this manner here, right, so the and we plot it in terms of the David-Rick stress, the void ratio. So from here, the void ratio, it will come to this state, right? Again, if it is a dense sand, all right, so when we will shear the dense sand, so the void ratio, if we plot it in terms of the void ratio, so that this is lower void ratio, all right, so and the void ratio will increase, all right, and then it will come to the, it will increase and come to the critical void ratio point. So this is the critical void ratio. All right, so this is due to the David-Rick stress. So David-Rick stress will increase up to this point. So this is the David-Rick stress. So plotting for void ratio with versus for David-Rick stress, we will get a curve like this. All right, and ultimately both the curve will meet at a one point. So that is the critical void ratio. So if we plot it in terms of void ratio and shear strain, we will have for dense sand this expansion or increase in void ratio, and for the loose sand we will have the decrease in the void ratio. Alternatively, if drainage is prevented, pore pressure will generate, all right, and the effective stress will reduce. It will come from this point to this point. In case of dense sand, all right, if drainage is allowed, expansion in volume. If it is not allowed, then pore pressure will reduce, all right, and effective stress state will come from this state to this state. So the effective stress in the soil will increase in the dense sand, and the loose sand it will decrease. So loose, we can say contractive behavior, dense we can say dilative behavior. All right, so loose contractive behavior, dense dilative behavior. So pore water pressure, reduction in effective stress and increase in effective stress. So this is the critical void ratio line. So these void ratios, so these void ratios for different confining stresses, if we plot, we will get the critical void ratio as we have discussed in our soil mechanics class. So what is said that, what Casagrande said that, so if a soil is on this state, in this phase, what we will have is, so the soil will, in case of undrained condition, pore pressure will generate. So this soil, this type of soil is susceptible to liquefaction. Whereas if the soil is in dense state, all right, so if there is undrained loading, there will be increase in pore water pressure, all right, and a decrease in pore water pressure, all right, and there will be an increase in the effective stress state. So what will happen is that the soil will remain, in fact, due to undrained loading in dense sand, all right, the soil will increase its shearing resistance, all right, so it will remain non susceptible to the liquefaction. So this is what he said, that if the soil is loose state, so it is susceptible to liquefaction. If it is in a dense state, it is non-susceptible to liquefaction. But so this is what he said. So we have the loose state which is susceptible, and we have dense state which is non-susceptible. But that is as further test was done. All right, further test was done. It was seen that this is not always the case. So here we have one sample, right, which is actually in the dense state. All right, and as according to Casagrande 1936, all right, it was non-susceptible. But this sample, when it was tested at the confining this amount of confining pressure, it was seen that this sample liquefied at 57 cycles. So we will see what is cycles. We will discuss what is cycles when we will come next, all right, in the next slides. Whereas this soil, now this soil, this is the critical void ratio line, all right, this is the critical void ratio line, which is this one, all right, so this should be susceptible, but this sample did not liquefy even after 10,000 cycles of application of cyclic stresses, all right. So then it was seen that the stress ratio, all right, so the shear stress versus the effective confinement, all right, so this stress ratio, it matters, all right, so it has a very high impact or very high a significant effect on the liquefaction of the soil. Of course, we are going to see that, all right, when we are going to do the quantification of evaluation of liquefaction, we are going to see that. So here at low confining stresses, though the soil was in the non-susceptible zone, it liquefied, and here due to the very high confining stresses, all right, so though it was in the susceptible zone, it did not liquefy. So this ratio, the cyclic, so the shear which we apply, so this is in a cyclic manner which we apply the cyclic stresses, all right, is very, the ratio to the effective confinement at that point, so this is the effective confinement at that point, all right, so is very much dependent, all right, so it affects whether the soil will liquefy or not, all right, so we will see that in the next slides. So before going on to the next slides, we have to define, first of all, we have been up till now using the term liquefaction. So up till now, whatever liquefaction we have used, the term, whenever we have used, we have meant the flow liquefaction type, right? So here what happens is that there is, so we know effective stresses as U, and we know shear strength of soil, or S is equal to sigma dash tan of phi dash for granular or sandy soil. So flow liquefaction is that type of liquefaction where there is buildup of very high pore water pressure, right? So the effective confinement, so here what happens is that we have a buildup of pore water pressure. So this excess pore water pressure builds up to such an extent that the effective confinement, right, effective confinement almost becomes zero, right? So effective confinement are reduced to negligible values or may be absolutely nullified, right? Therefore, so whenever now it is now, since this is the case now, right? So the soil actually now behaves as a viscous fluid, all right? Viscous fluid, right? So even a small amount of shear to the soil will result in continued deformation, all right, due to low residual static deviatoric stresses against which is the negligible or no residual shearing resistance of the soil, all right? So that is the flow liquefaction. So the soil is now, it is behaving as a fluid, all right, as a viscous fluid. Then sometimes what happens, that is this state is not reached, all right? So that intermediate stage we call cyclic mobility, all right? So there is buildup of pore water pressure, all right? And the effective confinement pressures are reduced to some negligible values, all right? And it is in a cyclic manner. So if you notice, earthquake is, the loading conditions in earthquake is in this manner, all right? So if in some cases, so only some amount of region of the loading is exceeding the shear stress resistance or shear stress of the soil, all right? So in that case, the remaining shear resistance or shear strength in the soil, they resist to the deformation. So the deformation occurs only when the magnitude of the cyclic stress, right? So when the magnitude of the cyclic stress, they exceed the residual resistance of the soil after initiation of liquefaction, of course. All right? And this initiation of liquefaction we call initial liquefaction, and we will see that this is a very important point, because from there on, how the soil will behave, how the deformation will continue, it defines that particular point. And in cyclic mobility, incremental deformation will occur, all right? And lateral spreading may also occur. So as the shearing will continue, so when it exceeds the remaining shear strength or residual shear strength in the soil, there will be deformation. And when the shear resistance, when the applied shear again reduces, again the soil will stabilize, all right? Stabilize means it will stop, the deformation will stop. Again when the applied shear stress will increase, again there will be deformation, all right? So it is cyclic. So that is why it is called cyclic mobility. Now initial liquefaction is, now during the course of cyclic stress application, what happens, there is buildup of pore water pressure. So the first cycle, so we will see when we are going to discuss the triaxial test or cyclic simple shear test. So in that test, what happens, we are applying the load in cycles. So after a certain number of cycles, there will be starting of buildup of pore water pressure, and there will be increase in the strains in the sample. So that point, right, that point where the pore water pressure, right, excess pore water pressure now it is equal to the effective confinement stress. So that is the start point. It denotes the point where, due to the application of the cyclic stress after n numbers of cycle, all right, after n numbers of cycle, the pore pressure buildup, excess pore pressure becomes equal to the effective confinement in the soil for the first complete cycle. So now the next cycle which is applied onto the soil, it is to the liquefied soil. So that is the point of initial liquefaction. So it becomes equal to the effective confinement soil for the first complete cycle of the cyclic stress. Now this has no implication concerning the magnitude of strain, right? The deformation in the soil, it has no, it does not define that, but it defines the point where there is change in the soil behavior. So up to that point, the soil was stiff. So beyond that point, now the soil will start changing the behavior from the stiff, solid, mass to a viscous fluid, all right, or I mean, it will start. I mean, there will be liquefaction. It will start deforming under even a small amount of static residual stress. So that is the initiation or the initial liquefaction, what we define. So flow liquefaction is total complete loss of shearing resistance or negligible value, and whatever static residual deviatoric stresses are there, now it is enough to cause continued deformation. So it is flowing like a fluid, viscous fluid, right, due to the static deviatoric stresses. Cyclic mobility is when there is deformation when the applied shear stresses exceed the remaining shear resistance of the soil. So there is some amount of resistance still in the soil. So when the applied shear stresses goes beyond that, so there is deformation. Again, when it comes below, it stops. Again, when it crosses that boundary, so here there will be deformation at these points, all right, and the soil will stop deforming, all right, and the deformation will stop at this particular range, all right. So this is the cyclic mobility. Then we have the initial liquefaction. So it is the point beyond, I mean, which defines from where the soil will change from a stiff soil solid behavior, all right. So I mean, from a solid mass to a viscous fluid kind of behavior. So that is the initiation of liquefaction. That point is very important as far as considering study of liquefaction is considered, right? So that is the defining point of liquefaction, start of liquefaction. Now, to study the criterion, to understand what are the different criterion for liquefaction of soil, so we have studied the triaxial test up till now. So we have studied that in the triaxial test there are three types of tests. So we have UU, we have CU, we have CU, and we have CD. So this is consolidated, that means this is drained condition. So here the shearing is under drained condition, and here the shearing is under undrained condition. So in cyclic triaxial test, most of the tests are of this nature. All right, the sample is consolidated. Why it is consolidated? So that we can understand the effect of initial consolidation, initial confining stress. This is a very important parameter as far as criterion for liquefaction of soils is considered. We will see how it is. So it is consolidated so that we can understand the effect of initial confinement, effective confinement on the soil. Initial effective confinement, okay. So effective, when I say the word, you kindly remember that it is sigma dash is equal to sigma minus u, right? So that is effective. This is effective confinement. And when we do the test, right, so as we have discussed in the previous slide, so most of the liquefaction is actually undrained loading condition. All right, so it is mostly undrained loading condition. So it is undrained loading condition. This is where liquefaction occurs. So sometimes it comes to here. So where the effective confining stress is zero. It is nullified. All right. Obviously, it is very. I mean, it is for a few fraction of minutes. All right. So maybe 10-20 seconds. All right, less or more. In fact, in 1897, when there was the earthquake in Assam, So that earthquake, it lasted for around 2.5 minutes, right? So it lasted for 2.5 minutes. So for that 2.5 minutes, whatever effect is to be considered, obviously it is totally undrained condition. So that is why there is development of pore water pressure. But we will see that there were some drained condition. There were some drained tests done on soil to understand the effect of the grain size and the permeability or the hydraulic conductivity of the soil and the dissipation of pore water pressure. If the pore water pressure quickly dissipates, definitely there will be no liquefaction of soil. We will see that as well. So we are going to confine with, first of all, the soil is consolidated, and whatever shearing is applied, whatever shear load is applied, that is applied in the undrained condition. So most of the tests are of the nature of CU. So as we have in our in our class of soil mechanics, we have learned that we, in the triaxial test, we apply the cell pressure. So the cell pressure is the water pressure which is applied to the water in the cell. The water pressure in the cell is transmitted to the soil through the rubber membrane, which is surrounding the soil, here, soil sample here. So the water in the cell cannot go into the soil, but the pressure in the water, so water is transmitted to the soil all around. So that is the cell pressure. Then we apply the, either we consolidate. So when we consolidate the sample, so we allow the pore pressure to dissipate up to certain value, So suppose we apply cell pressure of 200 kPa. So here the water pressure is 200 kPa, and then we allow the volume change to we allow the soil to consolidate. So the initial measurement was, suppose, 150 kPa. So initially the pore water pressure was measured at 150 kPa. Then we allowed some volume change, we allowed some drainage from the sample, drainage was allowed, and the pore pressure, it came down to 100 kPa. Pore pressure now it is up to 100 kPa, it came down to 100 kPa. So the effective stress in the soil is, so the effective confinement in the soil is 200 kPa minus 100 kPa, which is equal to 100 kPa. So that is the effective confinement in the soil. And then we apply the deviatory stress. Now in case of cyclic triaxial, now in case of monotonic test, what we do is we go on increasing the deviatory stress. We go on increasing 1, 2, 3, and so on. All right, and we get a stress strain curve for dense sand of this sort. All right, so we start from here, and the deviatory stress is going on increasing, and it fails, and then at it, the value stabilizes at one particular range. And similarly for the loose sand, it will increase, the deviatory stress will increase, and it will stabilize at a particular value. So that is the failure state of the soil, and there is continued deformation with no volume change at that point. All right, so have reached the critical void ratio, and there is continued deformation for the maintained deviatory stress at that point with no volume change. So here what we do is we apply cyclic deviatory load. Right, so once the deviatory load is increased to a particular value, suppose sigma d, then again it is released, right, and it is again, it becomes maybe 0, again it is applied, again it is released. So it is in a cyclic manner. So we denote it in a cyclic manner. So this is the cyclic deviator load which is applied in the cyclic triaxial test. So we have the sigma 3, which is the cell pressure, and we have the deviatory load, So initially it is increased, then again decreased, and again increased, and again decreased. So in a cyclic manner, it is applied. Now we have to replicate the stress condition in the soil. We have to replicate the stress condition in the soil. So Seed and Lee, 1966, what they said that when there is an earthquake, so when there is an earthquake, so the rock at the bottom of the soil, so there is a base motion which is applied. So the rock, it vibrates in this manner. So initially it moves in this way, then it moves in this way, then it moves in this way, then it moves in this way. So there is a vibration in the rock. Now that vibration, it moves as a shear wave. All right, it moves as a shear wave. It moves as a shear wave through the soil mass. So if we consider a typical soil mass here, so we have the sigma V, we have the sigma H, right? And then when there is an acceleration due to the earthquake motion, so there is a shear stress which is applied. So there is a shear stress in, first of all, in this direction, right? So it is deforming the soil element in this manner, and then again it deforms in the other way, right? So it reverses direction. So it is in this direction, then in the other cycle it reverses the direction, right? So there is shearing in this way. But here what happens, sigma V and sigma H is remaining constant. So that is why we call it the constant. That is why the researchers, what they called it is that this state is constant mean state. Constant mean state and extreme principal stresses. So if I draw the Morse circle of this state, so the mean stresses will be sigma V plus sigma H by 2, and it will be here. All right, and then there will be an extreme principal stress which will be applied, and what will happen is that at one cycle the Morse circles will increase in this manner, so the mean will always remain there. All right, and only the shear applied to the soil will increase. And in the other cycle, what will happen, in the next cycle, what will happen, the Morse cycle will again collapse to this state. Now the directions will change. So this is from this state to this state. All right, now again what will happen, the planes will change, the inclination of the planes will change, and now it will be in the other direction. But still, if we plot the Morse circle, it will again increase in the same manner. So the shear which was initially in the first cycle in the upward direction, so this is the first cycle, now in the second cycle it will be in the downward direction. All right, the planes have changed, that is. So the Morse circle will basically expand and collapse, expand and collapse. So the Morse circle will expand and it will collapse from the same point. So that is the constant mean and extreme principal stress concept. So that is what we have to replicate in the laboratory. So here we have the horizontal stress, vertical stress, all constant. So when there is an earthquake, there is only reversal of the shear stresses, only reversal of the shear stresses, right? So the Morse circle, the shear stresses will once move up, then move down. So the Morse circle will once grow from the same center, it will grow out and then grow in back, and then in the other direction. That means now the stress will be in the downward direction, so again it will grow. same magnitude, same radius, all right, and that is the constant mean and extreme principal stress. So that we have to define in the laboratory. So this part we will keep for the next class. So today is you just look into this, right? So this we will discuss in the next class. So in the next class, before continuing with the class, you kindly revisit what we have studied in the triaxial test, that is UU, CU and CT. Mostly this particular test. What happens in the the loading condition or the stress state in the soil. What happens in the stress state in the soil? How the Morse cycle will behave during the consolidated undrained test. So in the next class we will discuss further. So today we will stop here.